What you see here, a piece of paper with some stuff written on it and me pointing, is what you're going to see for the majority of the class lectures. Although there will be some demonstrations, really we're interested in the mathematics of the situations. Now let me comment that the three situations we just saw all actually related to physics. That's because physics is the simplest science to set up and analyze mathematically. We could set up economic models, we could set up social science models, or biological or ecological models, but they would be so complex that you'd lose track of the mathematics that we're trying to learn. The physics models are very, very simple, and we're not studying physics when we use physics models. Physics explains why the temperature behaves the way it does. Physics explains why the flow behaves the way it does. It explains why or how the pressure forces the water out and how the pressure changes with respect to depth. And we don't study the physics of pressure. We don't study the physics of temperature. We don't study the physics of mass density. We simply study the mathematics that you would use if you were going to do the physics. And that's the same mathematics that you use if you're going to do anything else. Any of the other models. Any field is going to use the same mathematics, and that mathematics is probably developed within the context of physics. In any case, the theme of the course is mathematical modeling, and we've seen three models here: a flow model, a temperature model, and a scaling model, where we increase the scale of a concrete ornament, and we might want to observe then how the mass of the ornament changes with the scaling. For each phenomenon we have here, there's a function that goes with that phenomenon. It turns out that the flow model is associated with a quadratic function, and you should recognize at squared plus bt plus c as the basic form of a quadratic. And remember the quadratic formula. Now if you don't remember that, we'll review it for you. Don't worry about that. This is the basic form of an exponential. Actually, there are about 3 or 4 basic forms that you could use for an exponential. This is the form I've chosen here: a times b to the t plus c. Turns out that b is a number less than 1 if you know something about exponential functions. B is less than 1 if the phenomenon is a decreasing exponential, and c is the value of your asymptote. But we'll do that in detail much later. This is a power function, and it's a power function with the appropriate power p. Turns out the third power in this case that we use to model the scaling that we just looked at. Now what we typically do when we have a function is we might observe the depth at 3 different clock times, actually at a bunch of different clock times, but we'll choose 3 clock times at which to infer what our depth is. And remember, we had y equals at squared plus bt plus c. We put the t for the time in here. For example, at 4 seconds the depth might be 12 centimeters. At 30 seconds the depth might be 8 centimeters, and at 100 seconds the depth might be 4 centimeters. So that we plug in the 3 times for t and the 3 depths for y, and we get 3 equations and 3 unknowns. Now we're going to square this. This will give us 16a, and the square of 30 will give us 900a, and the square of 100 will give us 10,000a. We'll have 4b, 30b, 100b. We'll have 3 simultaneous equations and 3 unknowns. And we're going to look at what we have to do to solve those simultaneous equations. Later on, we'll look at what we have to do to solve the simultaneous equations that you get from this model or this model. The algebra is a little bit different for these two models than it is for this. This one really has the simplest algebra, and that's the one that we're going to start out with as we analyze the flow model. So from the models that we've looked at, we can expand out into the study of equations and simultaneous equations, and then we move to algebra and graphing. Okay, what kind of algebra, what kind of graphing do we use? Well, the algebra that we use with quadratics, we use the quadratic formula a lot. In graphing, well, the shape of a graph is a parabola. Now we didn't use an example of a linear situation, although we will in the course. But if you have a linear function, you get straight lines, and the algebra is very simple. The main characteristic of a line is its slope and its intercept. You have the slope-intercept form, all that stuff that you should remember from your algebra course. You might not if it's been a while since you had algebra, and we'll certainly give you an opportunity to refresh yourself. Okay, exponentials and logarithms. Exponential functions, remember that was like what we saw for the temperature. Logarithms are the flip side of exponentials, and that's how we're going to define them. And this is where people's understanding usually gets kind of fuzzy. People don't really understand logarithms very well the first time they see them. So, we'll spend some time trying to understand what logarithms are and how they're related to exponentials. For the scaling model, I actually have power functions, and for power functions you have multiple graphs, a different type of graph for every different power, but the algebra is very simple. But we study the algebra that we have to use to analyze these kinds of functions. And then we move on to a broader study of functions. Okay, we talk about inverses of functions and combinations of functions. Actually, the logarithm being the inverse of the exponential function is one of the first inverses we study. We talk about composite functions, sums and differences and quotients of functions. How do you get the graphs of sums and differences and quotients and inverses? And then modeling by transformations, and that won't make a lot of sense to you right now, but it turns out that we can do this thing called a regression model, a best fit straight line. If we can take our nonlinear model, our parabola or our exponential or power function graph, and linearize it by some kind of transformation, make it into a straight line, we can apply regression analysis, and then we can take what we get out of regression analysis and bring the transformation back to the original and get a model. But that probably won't make any sense to you at this point. And then we have difference equations that describes what happens in one time interval based on what was there in the previous time interval. And again, that's something you won't have a lot of familiarity with at this point. We'll also study polynomials and polynomial approximations and some other topics. You can read the syllabus and see what some of those topics are, but this is the general structure that we're going to follow in the course. We start with mathematical modeling, we look at some basic examples, we look at how to model those examples, we look at the mathematics we need to model those examples, and then we expand out into other types of functions and other topics.